that is really hard, right? So in that it will be semi-custom. I mean, what will be the approach to design an analog circuit when there are too many transistors? That's my question.
Ma'am, to be specific, when it comes to full custom IC design flow, mostly it is manual placement and routing. It is that way. Semi-custom IC design flow only you have the option of doing the automatic placement and routing.
Okay, okay.
Yes. Here it is completely manual. Just
Okay, okay.
routing, we can make it automatically just by uh, I'll see if it is possible. This layer.
But let's
If
say
we
the
complete
inverter
this,
you showed, these blocks, building blocks, we can't just place it, the one that you showed now. I mean, NAND gate, all these cells, we can take it from the library, right? And then
yeah,
on
we
the
can
ground,
take it. We can take it from the library. Then there is no meaning in saying like it is full custom, right?
yeah, but my point is that we have all these different driving capability cells. Then why do we still do for a particular? I mean, the foundry has given everything well done. Then still, why do we do? I mean, can you explain when it is needed to do this kind of
Yeah.
manual?
Am I audible?
Yes, Sijo, you are audible.
Yeah. Let me. Yeah. Hi, madam. Good afternoon. This is Silvio Thomas. So what Naveen is elaborating here is how to prepare the standard cell library. So as ma'am already mentioned, we already have these things in the library.
Okay, okay. Yes,
Yeah,
yes.
as a
So this
standard
is
cell
the
library. So
foundry people is this is the approach. I mean,
yeah.
when they
So
give the
what?
library,
Yes, ma'am. What Naveen is saying, even Foundry will give the files also, standard cell library also. But for some companies, they have their custom designs. So if you want these things for your ASIC flow, if you want a standard cell library, this one engineer should do that one, right? So
okay.
hello. Yeah, as ma'am already said, we have inverters available for 1x drive strength, 2x drive strength, and also the AND gates, NOR gates, everything. So one has to do that standard cell library design. That is what this flow, that is what we are showcasing.
Correct, correct. So the foundry people gives this kind of cells. That's they do all
Yes,
this.
Foundry will give things, but it can be a generalized one. So if you are looking for a SRAM memory design, or so it can be depend upon which application you are doing for. So even if you look in the Foundry files, let's say for the DRC and LVS rule files, you can see there are specifically they have given different files for memory design application. For SRAM they have given it different. So you can see lot of the rule files depending upon the application. So Foundry can give you the standard cell libraries, but depending upon the application, maybe you have to rework it or you have to create your own standard cell library. Okay.
Okay, I understand. So if I want, let's say from the standard cell library, this inverter, I can drag and drop, right?
Yeah, you can drag and drop. There is no problem in that. That saves time actually. But those libraries, it is created in this flow. That is what we want to convey here.
Correct, correct.
Okay, okay. So
Thank
that
you.
saves the time of the ASIC designer. That's what.
Correct. Thank you. Thank you. So let's see this VDD VSS. They are higher metal levels. This right. But when it is at the cell level, it is metal one, and then through vias it gets connected to this finally to this higher metals, right? It is that way.
Yes, Mahesh. So it is actually GPDK. I don't know whether we have right information. But if you look at some real foundries like UMC or TSMC, there you can see they will give you the layer map information. So there is a pictorial representation, and right from the substrate to your top metal, what are the various layers available and what are the dielectrics in between. And if you have gone through, you can see in between metal 1 and 2 or metal 2 and 3, whatever it is, you can find it will not be a single dielectric. It will be a combination of two dielectrics, each with a different dielectric constant. Okay, so you can see all this device physics information or layer map information to be accurate from these foundry files. Okay. So depending upon that, actually we do things. So from GPTK, you may not be able to find this information basically. So they also give this elevation and also from the substrate in what elevation or what
So
height.
these files are left file. Are they left files or something else?
No, ma'am. I'm saying the PDF documents will be available, which will give you the information.
I see.
So
Okay.
in UMC it is named as layer map file. Layer map file. That is a
Okay.
document name. So they will tell you how the layers are arranged in your. Let's say it's a 1 poly 6 metal. Okay, that is 1 poly and you have 6 metals. So in 180 you can see the same. So 1 poly 6 metal means you have 1 poly and 6 metal layers. So metal 6 is the soap metal. So how that hierarchy goes in the
Correct. Correct.
foundry, that they will give the information.
I see. Okay.
Okay, okay. So if you look at real foundry files, you can find all this information. Also, they will give the dielectric constant, all those things. So during EM simulation, maybe in momentum or some other tool, you may require to give this device physics or material information to the tool. So that
For
time, those files are required.
for GDS2 up to that, we need all these files from the factory then, and then it
Correct,
is
correct. Yes, ma'am. Right, ma'am. Right.
okay. Thank you. Thank you.
Yeah, yeah. Thank you.
Thank you, sir.
Yeah.
Hello, sir.
Yeah.
Yes,
Hello,
ma'am.
sir.
Yes.
Can you hear
Yeah.
me? Sir, we have done this all circuit layout design with respect to NN parameter selection, isn't it, sir? For process corner.
Yes. Yes, ma'am.
Sir, can we use the same one and go for testing it for other corners also, SS and
Yeah.
that is
Yeah.
fast,
Yeah. Naveen.
slow?
Yeah.
Yeah.
Yeah. Yes, ma'am.
We never
Yes, ma'am.
thought
So
process.
I can give an
Ah,
idea on that, ma'am. I think little bit
ah,
confused here. So
ah.
we don't have a different layout for each corner, madam. Okay.
Okay, sir.
Corner
Mm.
comes when it goes to fabrication. Okay. Suppose you have designed the same inverter one next, it goes for fabrication. Okay.
Ah,
So
ah.
so when it comes to fabrication, then only we will characterize it as different corners. Okay. Your all the transistor will not be in the same corner. That's what the idea is. Okay. So depending
Right,
upon each corner, the performance also will vary. Okay.
right,
So to
right.
find that variation, what you have to do is in the schematic part, you have ADXL option, that is analog
Right.
design environment is there, as we have shown yesterday. So I think
Yes.
today, if time permits, at the end, we can show you how to simulate the circuit for, now we have shown it for the nominal corner, or we can say typical corner, but we have slow, slow, fast, then fast is there. Okay.
Yeah.
And also you have variations
Yeah.
with voltage and temperature. So temperature,
Okay.
we can say, okay, temperature also variations are there, minus 40 to 125 degrees Celsius, we have
Right.
variations. And also the supply
Hmm.
voltage, you can go for whatever, plus or 5% variation, whatever. Those things we can do in the tool actually. Okay.
Okay. Okay.
So we have options for that. Okay.
Okay,
So if
sir.
you want
Thank
to
you.
see how the layout parasitics also, how the things will affect your circuit, what you have to do is you have to complete the layout for a particular circuit. You have to extract things, extract the parasitics, back convert it to your schematic design. Then you go for the corner analysis. So that will give you the complete picture with taking into consideration all your parasitics also. Okay. Still,
Right.
I can't say in real silicon it will not be 100% accurate values, but it can be related to up to a 90%, 90 or 95% accuracy. Then comes you have the Monte Carlo analysis and all. Okay. There also you can go for the bell curve, standard deviation. You can look up for the yield and all. So all
Yes.
those things actually will give you the correct picture. Okay.
Mm-hmm.
So
Okay.
from that actually we define the data sheet parameters. Like, so whatever the worst case you get, that comes in the data sheet as VDKs are told. Okay.
Yeah,
So
yeah.
suppose the gain is in between 50 dB to 100 dB, whatever the, you can see typical, nominal and maximum values given in the data sheet for every parameters, electrical, DC parameters and AC parameters. So these values we are
Okay.
extracting from these simulations basically.
Okay. Okay.
Okay,
Thank
that
you.
we can show, ma'am. We can show at the end of the
Ah. Okay.
session
Okay.
today. We'll
Okay.
run a quick simulation for the NMOS itself. Okay.
Okay. Thank
Okay.
you.
Okay. Thank you. Thank you.
So
Naveen, I
hope
think you
the
can
queries
continue.
are.
We are running out of time.
Yes, Sijo, yes. So let us continue with whatever we have been doing. Okay. Uh, so just before the break, okay, we have created the rail for VDD and VSS. Okay. And then we got the PMOS and NMOS transistors here, and then we did the internal routing. That is, we connected the drain and drain of PMOS and NMOS, gate of PMOS and NMOS, and source of PMOS and NMOS with VDD and VSS respectively. Now let us go for the pins. Okay. So coming to the input pin, okay, so here we have already got the pin, but we need a wire, right, in order to connect between two different layers. Okay, so we can instantiate the wire. Okay, so for that we can go to create and then select wire. Okay, so here it has to go from metal 1 to poly, right? So I'm selecting that and I'll click on hide and place it over here. Okay, so I can get it here. Okay, first let me rearrange this. Okay, so that it has to be at the center of this routing grid, right? So let me check it out. Okay, so just a second. So the width of the metal layer that we have here is we can measure this 0.3 micron. Okay, so it has to be exactly at the center. Okay, so I have got the measurements. Okay, so it is just a second. So it has to be, let us go for a butting process. Okay, so this has to be at 0.81. Okay. Okay, so this is fine. Okay. So yes, so we have got the input pin in correct alignment. Okay, now let us check the width of this wire. Okay, by using the ruler. Okay, so it is 0.6. Okay, so it will come somewhere around 0.96. Okay, right. So we have got the wire. Okay, now we have to connect these two things. Okay, by using a poly layer. Okay, so just go for a polygon. Okay, you can also make connections by using a polygon. Okay, shortcut for that is shift P. Okay, so you can create it like this. Okay, based on whatever shapes you want. Okay, but rectangle you cannot change the shapes, but with the polygon you can change the shapes. Okay, fine. So input pin is done. Now let us come for the output pin. Okay, so here it is 1.98. So it has to go up till 2.13. Okay, so yes, here it is more of is close. Okay, so this is exactly the center, and surrounding this you need to create a metal. Okay, so a metal enclosure is 0.1. Okay, so I'll go for this all the four sides and have the enclosure. Okay, so I'll go for a metal one, create a rectangle. Okay, so I'll go for partial select and do the metal process. Okay, done. So input and output pins are done. So the next one is your VDD and VSS. Okay, so I'll select the VDD pin. Okay, and bring it to the rail. Okay, it is not like it has to be exactly at the center. It can be placed at any one of these contacts. okay, placed to any one of these contacts so that it is okay. So I'll get it here. Okay, so measure 0.05. Okay, and I'll go for a button. Okay, done. So VDD is also done. And we have the ground terminal. Okay, so VSS. So we have got it here. Okay, so I'll go for a button. So full select. Okay, done. So your layout, standard cell layout is now complete. Okay, so surrounding this, you have to create your PR boundary, placement and routing boundary. So for that, let us go to that layer. We have a layer for that here, PR boundary. Okay, so go for Shift P and create the PR boundary for your standard cell unit inverter. Okay, done. Okay, so after completing the layout, you can also disable the template. Okay, so just you can go to view, select background and go for off. So it takes out the template. Okay. So now you can see this is a standard cell layout for the inverter X1. Okay, so one more thing we have to do. Okay, so we have to merge this, otherwise your bulk connection for NMOS transistor won't be there. Okay, so just that one change alone is there. Okay, okay, done. So after completing, I'll save the layout. Okay, now let us go for the physical verification process. Okay, so for that, first let us select the library file. Okay, because layout we have done it in Ashura, sorry, the virtual layout editor. Okay, but the tool for physical verification is Ashura. Okay, it doesn't understand whether it is a transistor or metal one layer. Okay, and it doesn't know the rules. Okay, so we have to map it with the library file. Okay, so I'm going to just browse the technology library file. Okay, so for that I'll go into Ashura and I'll select technology. Okay, here you can browse it. Okay, so it will be available within the foundry. Okay, this double dot, okay, which is used to go back to the previous directories. So I'll go back. So within the CAD folder, I have foundry. Okay, and within that analog 180 nanometer and Ashura underscore tech.lib. Okay, so select OK. Library is mapped now. Now let us go for DRC. Okay, so I'll go for run DRC option. Okay, here you can make sure of the cell, okay, with which you have to, within which the layout is available. Okay, so you can also give a run name. Okay, so for example, I'll name it as S.P.I.T underscore DRC. You can give any name. Okay, and select the technology. Okay, here you have a drop down. So here from this drop down, you'll have to select GPDK 180 and select OK. Right. So it will complete the DRC run. Okay, and if you select yes, you can see the result. Okay, so no DRC issues. Okay, so the next step we'll go for LVS. So again, I'll go back to Ashura. I can see run LVS option. Okay, so here you can see. Okay, the location of your schematic and layout, because it is the comparison between schematic and layout, right? So whatever is there in your schematic, like devices, connections, pins, ports, etc., everything should get replicated in your layout. Only then your schematic and layout are similar, okay, or they match with each other. Otherwise, it is a different thing. So there is no use in going for going for an LVS. Okay, so here also I'll name it as, I'll give a name for my LVS run. Okay, S.P.I.T underscore LVS. Okay, and now you can select OK, right? So the process is getting executed in the background. Okay, so you can see, okay, so everything is fine, zero mismatches. Okay, everything is matching with each other, and if you select yes, okay, you'll get the complete result, schematic and layout match with each other. Okay, so next one is the parasitic extraction. So I'll go into Azure again. Okay, and I'll select run Quantus QRC. Okay, so here what you'll have to do is in outputs you'll have to select extracted view. Okay, and then you can go back to extraction, select extraction type. So whichever you want, whether you want only resistor or capacitor or RC or RLC, whatever is required, okay, you can select that. As of now, we'll go for RC. And here you can mention the reference node, whether it is with respect to VSS or VDD, whatever it is, we can mention the reference node. Here it is VSS. So I'll select OK, and the parasitic extraction is going on in background. Okay, so you can see now the Qantas QRC run is completed successfully, and the output is in this library cell and view. So if you go back to the library manager, okay, so let me go back to the library manager. Okay, so here you can see this is the schematic and the layout, okay, that we have done. Okay, so here you can see the AV underscore extracted. Okay, you can see 1 underscore INV SPIT. So if you open this, make a double click to open this. Okay, so you can see this is how it looks like. Okay, so if you zoom in, you can see the parasitic resistors and capacitors. Okay, fine. So if you wish to check out the values, okay, so you can go for Shift F. Okay, if you give Shift F, then you can check out the values of these parasitic resistances and capacitances. Okay, fine. Now we have to go for the back annotation process. Okay, so we have already created a test circuit. Okay, so we have it over here. Okay, so this is config view. Let me remove it. Okay, so we have the schematic over here. Okay, currently what we have within this circuit, if you make a double click, you can check what this symbol represents. Okay, so I'm opening it in a new window. So you have the inverter that you had created. Okay, so now what you have to do is, okay, so we have some changes over here. Just a second. So let me change this symbol because dimensions are not correct. Okay. Okay, fine. So I'll check and save this. If you open this now, so what we get to see? Yes, now it is fine. Okay, so I'll create a configuration view. Okay, so I'll select the schematic. I'll go to File, New. I'll create a new cell view, and in Type I'll select Config. Okay, in Type I'll select Config. Okay, and go for Use Template first. Select the simulation engine that you made use of in order to simulate your design. Select OK, and the top cell view has to be schematic. Okay, select the top cell view to be schematic. Now go back to tree view. Okay, select the instance. Okay, this is the instance number, okay, of your inverter. Okay, select that, make a click, go for set instance view, select AV underscore extracted. Okay, now right now you can see, if you expand this, you'll be able to see only the PMOS and NMOS transistors. Okay, so I need all the parasitic components to get imported over here so that I can check its impact on my schematic. Okay, so I'll make a right click, go for set instance view, and select AV underscore extractor. So all the parasitic resistances and capacitances get imported over here. So I'll update my circuit. Okay, so I'll go for view and select update. Sorry. Okay, and then select OK. Now go for open. Okay, once you select open, it should bring back your test bin circuit. Okay, so this is the test circuit, right? So it should bring back this. Okay, now load your simulation state. So I'll go for launch ADEL. Okay, and then I'll load the state that I have already saved, right? And rerun the simulation. Okay, so that's it. Okay, so how do you check impact of your parasitic components? Okay, so you can measure the propagation delay. Okay, measure the propagation delay here. Compare the propagation delay for pre-layout as well as post-layout simulation. Okay, and check its impact. Okay, by this is one of the methods of how you can check the impact of your parasitic components. Then you have some other methodologies also. This is the most basic one and most widely used option also. Okay, so finally you can generate the GDS file. Okay, so let me show that. Okay, so from your Virtuoso command interpreter window, CIW window, so I'll go to file, okay, and then go to export. Okay, file, export, and then select stream. Okay, so GDS file is also called as stream out file, so I'll select stream. Okay, and here you can see, okay, stream file, library, top cell, and the view is layout. So what is the meaning? So next to library you have the browse option. Go to that. Okay, select the cell which has your layout. Okay, so this is the cell which has my layout. Okay, S.P.I.T, and here is my layout. Okay, so I'll select OK. Right, so I've got my GDS name also, stream file name also. You can give any name, but it should have an extension .gds. Okay, so now select the technology library, which is GPDK 180, and select translate. Okay, so the GDS file has been generated. Okay, and this is the log file. Okay, so GDS file is a binary file, so you will not be able to view its contents. You have a separate tool to extract it and check it out. Okay, right now we'll not, this is the log file. Okay, but we'll not be able to open that particular GDS file over here. Okay, let me check. Okay, anyway, we'll be having the name of GDS file. So 1_INP_SPIT.GDS. Okay, so let us search for it. Okay. So you may have it somewhere over here. So you have it here. Okay. So if you open, so this is the reason I told you. Okay, so this is a binary file, and you will not be able to have a view of its contents. Okay, you have a separate tool for this. Okay, so that's it from the session. Okay, that's it from my part. Okay, so let me go for a quick recap, okay, of what all things we have done. Okay, so we have taken an inverter as an example. Okay, by taking that, we created an basic inverter standard cell. Okay, that is we call it as unit inverter because of its drive strength 1. Okay, we characterize the PMOS transistor and NMOS transistor. Okay, and we went on through the channel resistance, effective channel resistance, and effective gate capacitance. Okay, and through that we obtained the ratio of mobility and got to and got the ratio of it, and then we measured the width of PMOS transistors. Okay, and then we created a schematic symbol. Okay, generated a test circuit. We created our own test circuit. We executed the simulation. We did a transient analysis, DC analysis. Okay, we plotted the drain current. Okay, and then we measured the switching potential. Okay, and then we went on for propagation delay calculation. Okay, by measuring TPHL, TPLH, both the options, and then we went on for the layout creation. Before going for the layout, we created a template for the standard cell in to maintain the height of the standard cell, height of the particular standard cell. We created a template by going through the basic DRC rules. Okay, for and this will be available for all the almost all the technology news. We have to go through the document. Okay, and once that is done, okay, we created the template. We measured the pitch. Okay, we considered a wire to wire pitch. Okay, and then we created the layout. Okay, first we created the VDD rail and VSS rail. Okay, for the width of VDD and VSS rail were approximately 1.08 micrometer. Okay, and then we instantiated the PMOS and NMOS transistors. Okay, completed the internal connectivity. Okay, then we instantiated the pins. Okay, completed the remaining connections. Then we went on for the physical verification process. We started with DRC, LBS, and finally we went for parasitic extraction. Okay, and then we imported those parasitic components within the schematic. Okay, in order to check its impact. Okay, so once that was done, we ran the simulation. Okay, and then we checked out the results. Okay, by comparing the pre-layout and post-layout propagation delays, you will be having an idea of the impact of parasitic components on your schematic. Okay, and finally we generate the GDS file. So till this, in case if you have any doubts, you can let me know through the chat box. So as of now, I'll hand over the session to Sijo, okay, for analog layout process. Okay, yeah, over to you, Sijo.
Thanks, Naveen. Thanks. Am I audible,
Yeah.
Naveen?
Yes, you are audible, Sijo.
Okay.
So yes, the PPT is ready. So Sijo, just give me a minute so that I'll
Yeah,
close all
sure.
the remaining windows.
Sure.
Shijo sir, good afternoon.
Good afternoon, sir. Good afternoon.
Good afternoon. Shaila madam is a little busy today, so she has not joined the session. But she has asked one question to me. Like, yesterday, VDK sir was supposed to tell her about and he has mentioned two papers. Sir has mentioned on using GM by ID for characterizing the transistors for required device parameters from circuit specifications. So she was asking the details of those papers. Actually, she messaged me that will you please ask the details of those papers?
Yeah, it is from Gray and Mayer, sir. And one more other poll. Let me check with check the credentials properly, sir. I will get back to you.
Yeah. Please.
Mostly by end of the day today.
Okay.
Yeah, it is from Gray and Mayer, sir, but it's an old publication.
Actually, it's old publication.
Yeah, it's very old actually. So I will get the credentials.
Okay, sir. Okay.
Yeah.
Yes, Joe, you can.
Thanks. Yeah, once again, good afternoon, everyone. Myself, Joe Thomas. So, welcome to the third session on analog IC design. So, today we'll be discussing on analog layout design, which are the matching techniques, and we'll move to a illustrative layout design of a 7-pack op-amp, for which we designed the circuit perspective. We looked at the circuit perspective yesterday, so we'll try to make some sense on layout also today. So let's quickly move to the session agenda. Naveen, yeah. So as I said, it will be a brief introduction into analog layout concepts. So we'll be going through analog layout, basically what is the need for matching and different kinds of matching techniques, basically proximity matching, interdigitization, common centered layouts, and also we'll look at what are the effects of mismatch. Then finally we'll look into the tool illustrative session for a layout of a 7-pack op-amp. Okay, so coming to the MOS transistor matching. So as you all know, most of these analog circuits we make use of a matched transistor. Okay, so basically they are electrically equivalent components. Okay, we can say as an example differential pair that basically relies on matching of gate to source voltage, that is what we call as VGS. Also you can find the current mirror, many applications for current mirror. There also it is a best example where we apply the matching techniques basically for the drain currents. That is what it is significant for. So biasing conditions. Okay, so basically we have voltage and current matching. Okay, so biasing conditions for voltage and current matching, that differs basically. So if you look at the Sheeman-Hodge equation, you can see the delta VGS. Okay, that is a change in VGS for a matched pair of transistors that can be related to delta VT minus VGS of delta K by 2K2. So I'm not going in details of the equation. You can find the published papers on the same also. So this is, we are looking for a voltage matching. So here we can see the voltage matching depends upon the gate to source potential and also the threshold voltage of your MOSFET. So coming to the current matching, okay, so also from the same Sheeman-Hodge equation, we can see in the next slide. Yeah, you can see the drain currents of it for a matched pair of MOSFETs. Okay, you can write it as constant K2 by K1 into 1 plus 2 delta V by VGS T1. Okay. So what we can see is voltage matching of MOS depends upon the matching of threshold voltage. Okay, and when it comes to current matching for MOS transistors, that basically depends upon the transconductor. Okay, so coming to the next slide, we will discuss what are the causes of mismatch basically. So there are many causes for the mismatch. It can be basically due to the happens in the manufacturing process. So there we can list it as geometric effects. There can be a random variations, okay, in the match pair of resistors dimensions. Then process bias. There can be bias variation. Okay. Also, there are interconnection parasitics. As we already have seen the layouts, okay, in the last session, we can see we are making physically implementing it using metals, wires, polysilicon, everything. So we have interconnect wires, everything. So definitely we have parasitics due to that one. That is what we extracted in the last session at the end of the last session. And also we have pattern shift edge variations will be there. That is basically from the comes from the manufacturing process. And also during the photolithographic process, you can find there can be many effects due to photolithography process also. So again, we can see few more diffusion interactions, hydrogenation, okay, mechanical stress, and also issues with the packaging chip. Okay, there can be stress gradients such as piezoresistivity that becomes significant when it comes to the layout of resistors. Okay, and also the gradients and centers. Okay, so we can see how these variation in these things, how it will affect our layout. Okay, also we can see the size, shape, and also the orientation. So till now what we have discussed, okay, is due to the basically due to the process variation. So okay, so if we come to the next slide, yeah, also while doing the layout, okay, as a layout designer, okay, these things are in our hands. Basically whatever I told in the last few slides, that comes from basically from the manufacturing process actually. So when it comes to the layout, these are the things basically process mismatch. So these are things which layout engineer can contribute so that we can make sure that the matching overall matching of my layout, okay, remains better. Okay, so there actually we can see the size of the monster. As you all know, higher the size, okay, higher the area, the effect of mismatch, okay, the contribution of mismatch, the effect of mismatch on the entire layout, that ratio will be less. So always the size, also the shape, okay, and the orientation, all affects matching. Okay, and obviously long channel transistors match more precisely than short channel. Okay, so now let's discuss about few instances where matching uh, can be crucial. Okay, so if you move to the next slide, yeah, so let me give you some thought process here. So we can see two identically electrically equivalent components A and B here. Okay, we have drawn them equal identically. So they are A and B. They are of similar shape, area, perimeter. Everything is equivalent. Okay. So the question is, are they matched? Okay. So when I say A, B, I have one more component here, C. It can be anything. It can be a MOSFET or resistor, passive, anything. It can be active or passive device. That is not relevant here. So as I already told, A and B, that is identical in similar in shape, area, perimeter, everything. So whatever the few points that causes mismatch, that is already taken care of here. Okay. But still the question is whether A and B, that are the devices to be matched, and are they matched in this layout? Okay. So the answer is no. Why? Why it is not? As I already told, they have similar shape, area, perimeter, everything. Then what is the problem here? Why A and B are not matched to each other? So the problem is, you can see they don't have the identical surroundings, okay, around it. You can see if you look at the A, okay, onto the left he is having A, but onto the right he is having C. So he is having different conditions, okay, surroundings, okay, conditions onto his left and right. So we can't say it is a matched layout here. Okay, so let's see what can be done to overcome that. So if we go to the next slide, okay, yeah, for the same set of components, that is A and B, which are identical in area, perimeter, all the thing constraints whatever I defined in the last slide remains the same. The only thing we were concerned about was the identical surroundings. So what I did is I use dummies. Okay, this is where the significance of dummy devices comes into picture. So to keep the identical surroundings, to keep identical surroundings for both A and B, which are the critical devices which are to be matched, what I did is I attached dummies. So now what happened is I have attached the identical dummies. So onto the right of A, and left of A, also on top and bottom, I have identical surrounding. I have attached identical dummies. Okay. So now what we have done is we have shown what is the significance of dummies, and we have made the match pair of the A and B devices, okay, more match in terms of identical surroundings, and all other things such as shape, area, perimeter, anyway it is taken care of. Okay, so we'll discuss these things in detail. Okay, so now let's move to passive. Okay, how yeah, let's discuss some basic things on passive. So as you all know, all materials, okay, possess a resistivity. Okay, so I can just tell you typical resistivity basically for the 180 nanometer technology. Okay, the values can be different depending upon the foundry. Okay, because in each foundry the metal layers they are using will be different. So if you can see UMC, it will be aluminum. Okay, so in other places you can see different metals. So it depends upon the foundry, the metal layers material can be changed, and accordingly the sheet channel resistance, that is what I have shown here for the metal, that is 0.1 ohm per square, that also can be different. Okay, and also you can see for N plus contacts polysilicon, for N well, okay, and also low dop polysilicon. Okay, what are the sheet channel resistance? So where we can find all these values, that is the next question. Okay, so as a layout engineer, why I have shown these values is this is actually significant. Okay, so we should know how my shape or the length or the dimensions which I take to wire the transistors. Okay, we are making we are realizing those using the metal layers. So we should be knowing the contacts or whatever I use in the layout, right? How it will affect my layout, how it will affect the entire RC time constant, or the how much parasitic resistance it may contribute to my entire system. So as a layout engineer, you should have these um, rough picture in your mind. Okay. Okay. So if you move to resistance, as you can see, if you move to the next slide, in the library, if you can open your GPDK 180 library, okay, I think yesterday we have shown we have many resistors available. High res poly is there. Okay, polysilicon resistors are available. So many kind of resistors are available. So I'm just listing each one here, and there. So when we say poly resistors, the advantage is here they have actually higher sheet channel resistance. Okay, so if you want to incorporate a high value of resistance, maybe as we can say 20K or 30K, and if you are really constrained about this area of your chip, okay, IC or the layout, then what you can do is you can go for poly resistors. So which is having a high sheet channel resistance. Okay, so that will help you to reduce the area. So we have basically silicidated poly resistors, okay, so which have actually less sheet channel resistance compared to the non-silicidated poly resistors. Okay, and accuracy also you can see definitely on all the resistors whatever you fabricate in the foundry, they are not ideal. There can be variations. That is what we specify as a tolerance limit here. Okay, so silicidated layer actually after salicidation, okay, what happens, titanium salicidation, what happens is it will actually reduce the effect, parasitic resistance effect due to contacts, vias, everything. That's why the one with the silicidated poly resistor, which is having less sheet channel resistor compared to non-silicidated one, okay, which is having higher, like 1K per unit area. Okay, so the advantage of silicidated ones are small parasitic capacity to substrate, okay, superior linearity, but it obviously a high cost due because we need to get an extra mass, okay, which we needed to block the salicide layer. So these are the advantages. So we also have diffusion resistors. Okay, I'm just giving you some rough picture about the values. Okay, how the sheet channel values come with each other. So here it is actually almost equal to your polysilicon resistor. It is also having 1 kilo ohm. That is almost 1000 ohm per square micrometer. Okay, so large parasitic capacitance between N-well and substrate. That is what we are making use of. So resistance is strongly the terminal voltage dependent, and it is obviously non-linear. Okay. When it comes to the error percentage, the error is actually the accuracy is bit less here. You can see it is having plus or minus 40% tolerance. Noisy has all the disturbances, but not noise from substrate can be coupled directly into resistors. So this is more prone to noise effects. So it is not recommended where noise is a significant parameter in your circuit. So coming to the layout, so I have given a few idea, just give you some numbers on the sheet channel resistors of URLs. I have not listed all the types of resistors. So you can find many other types of resistor other than poly resistor or diffusion resistor. You can find many things. So I'm just listed some of the common ones which we use in the layout. So coming to the layout, okay, standard resistors, what you can see is we mostly will try to avoid the 90-degree angles, okay, at the bends basically. So we always look for a 45-degree or a curve shape. So what happens is you can see the layout structure in the one. The first one is with a 45-degree angle at the bends, and the other one is having the sharp edges 90 degrees. So what happens is resistance at the corner is okay, it cannot be estimated accurately. So even though you do the EM analysis and all, okay, and estimate those resistance, okay, it can be still there can be a big gap in the accuracy. So always it is better to go with a 45-degree angle, because in the when we do go for the 90-degree angle, okay, at the corners basically do meshing to analyze when we do the EM simulation. So their accuracy will be go for a toss. Okay? And also the current flow through the corner is also not uniform. And also when we go for the fabrication, there can be possibilities where we fabricate the sharp edges, 90-degree bends. There can be some etching issues also at that. It will not be the accurate shape as 90-degree bend. So those things will come back in the next coming slides. Okay. So I have shown you, okay, which kind of layout we make use of. Okay. So Naveen, can you move? Layout of match. Next slide. Yeah. So this is where you can see the figure, okay, for a standard resistor with a 45-degree angle and the one with 90-degree angle. So if you move to the next slide. Yeah. So layout of match resistors is what we have shown here. Okay. So it is basically an interdigitized layout, okay, which minimizes the effect of process variation in X direction. So how it minimizes the variation will come back on the later slides. And what is interdigitation also, we will come back on that point in the coming slides. Okay. So just keep in mind we are doing interdigitization here. So suppose you want to match two resistors R1 and R2. So what we have done here is we have arranged in a pattern, in the digitized pattern. Okay, we can go for, you might have seen many patterns like A or A kind of things. So we'll come back to those interdigitization techniques for matching in detail in the coming slides. So we also used here dummy resistors at the end. You can see the dummy resistors which I have shown. If you look at the figure on the right side, you can see at the end I have attached dummy resistors. Okay. So dummy resistors basically that doesn't have any contribution to the system performance, but for matching, from thinking from the matching perspective, in order to provide identical environment, okay, for all the matched devices of interest, we make use of dummy. Okay, the same thing we have seen for the MOSFET, okay, in the beginning actually. Okay. So if you move to the next slide. Yeah. So these are the basic guidelines, okay, when you deal with the layout of the resistor, when we do the layout of this. Okay, so definitely if you want to match two resistors, obviously it is recommended to use the same material, okay, whether it is high-res poly or we can use diffusion, whatever, but it should be a same material. Then you can go for identical geometry and same orientation. Okay, so if you are going for a say orientation of vertical orientation for R1, then obviously it is recommended to use the same orientation for R2 also. And also try to keep the resistors in close proximity, okay, so that and also make use of interdigitized arrays of resistors as we have seen in the last slide, okay, and maybe you can use the dummy elements also, okay, to in order to provide identical environments for all the matched pair of resistors, okay, and also piezoresistivity, okay, is also a concern, okay. So if we are making use of resistors with some piezoelectric material, and if you place that resistor in a high stress area, okay, the stress can affect the resistivity, sheet channel resistance of your resistor. So it is always recommended, okay, in the PCB layout or wherever, or in the analog layout, it is to avoid place resistors, okay, in a low stress area, and also place resistance away from your power devices. These all things comes in when it comes, okay, for a when you go for a PMIC design, okay, and also it is recommended to have a electrostatic shielding. So now we will move to the next passive important passive we use, that is capacitor. Okay, so if we move to the next slide, Naveen.
Yes, Joe.
Yeah,
Hello.
next slide. Next slide.
Yeah, I've changed it. It's capacitors, right?
Yeah, there's a delay in the
Okay.
okay. So when it comes to capacitor, okay, so naturally there are capacitor between each layer of metal, polysilicon or silicon, okay, whatever it is. So the substrate in between the metals you use and the substrate, there will be obviously there will be a capacitance. Those parasitics is what we extracted, okay, during the QRC quantus RC extraction in the last session, okay. So why we have capacitors in between? So what is the dielectric in between? Obviously, if you look at the layer map files from the foundry, okay, you can see in between each layer of metal or each layer of polysilicon, in between each layers, okay, you can find dielectrics, okay. So dielectrics, okay, which have a particular thickness that can vary from 0.5 to 1 micron thickness, okay. So these all things actually together contributes, okay, parasitic capacitors in your layout, okay. So the key parameters when we look at the capacitor layout, key parameters are basically linearity, okay, parasitic capacitance to substrate, then series resistance and resistance of capacitor plates, okay. Obviously, if you look at the, if you model the your capacitor, okay, even if it is a MIM cap, metal insulator, metal cap, or PIP cap, poly insulator, poly cap, whatever it is, you can find. If you look at the modeling of that device, as you can see, there will be obviously parasitic resistance also associated with it. So these all things become significant if you are going for a high-speed design, okay, where the propagation delay of your entire design, those things become a significant parameter in your device. Then these things all things comes into picture. So as a layout engineer, okay, for a high-speed design or whatever it is, okay, you should be keep prime priority to these parasitics. Okay, basically the capacitance per unit area and also the. So basically we choose actually from the available capacitance like min cap or peak cap, okay. So if you use min cap, maybe to get the capacitance per unit area is bit less. So if you want to use min cap, it may take more area, but there actually the linearity, okay, and all the stuffs are better. So we choose different capacitor models depending upon the application. Then if you move to the next slide, so different types of in the IC capacitors I'm introducing here. So one is the poly diffusion capacitor, okay, like you see the diffusion resistor, okay. So it has a tolerance of accuracy of 20% variation, okay? And also you can see the capacitance per unit area is 6.6 to 0.8 femtofarad, okay, per micrometer square. Okay, and matching accuracy is up to 0.2% variation can be there. Okay, and most capacitors, okay, uh, we can also see most capacitors. That is the one we used yesterday. I think if you remember, we used a 3-terminal NMOS cap, okay, for the as the compensation capacitor in your 7.5 op amp. So there was a 3-terminal NMOS capacitor. So obviously we are making use of MOSFETs, active devices to realize your capacitor. It's a stable capacitance in strong inversion, and non-negligible channel resistance is there. So it lowers the quality factor Q. You can find the quality factor for each passive, basically for inductors and capacitor, which becomes more significant if you go for RF designs, and quality factor is a certain parameter there. Okay. So for most capacitors, the capacitance per unit area that differs from 0.6 to 0.8 femtofarad, and it is reasonably comparable accuracy with the polydiffusion capacitor, and matching is bit less here, 0.5 variation you can see. Okay, I have few more capacitors in the next slide. So which are basically poly capacitor, poly insulated poly. That is what we call as tip cap. You may be able to find these things in the library. Okay, I'm not sure whether we have it in GPDK18. So again, if you look at the values for the capacitance per unit area, it ranges -3 to 0.5, a bit less compared to the MOS cap, and matching is almost compared with the MOS cap. We also have metal poly capacitor, okay, and also we have metal, that is a min cap you can see, but it will be as I said in the beginning, capacitance is small, that is capacitance per unit area is small. You can see compared to other ones, it is very less value, that is 0.02 to 0.04 femtofarad per micrometer square. But matching is good there. That is the main advantage. So as I said, if you are looking for a better matching and you are okay to sacrifice on your area, okay, and area is not a constraint, obviously the best option is min cap. So it's up to the layout designers, and it will be a combined effort from circuit designer and layout designer, okay, to select which capacitor model I should use depending upon the application. So coming to the next slide. So as I told, when we discussed about the resistor layout, I told like we generally we try to avoid that 90-degree corners, okay, because it is tough to measure the will not be current will be not uniform there, and it's also very tough to measure the resistance at the end when we do the EM analysis and measure. So what is the problem if you go with a 90-degree corner or -270-degree corner? That is what you can see on the left corner of your design, okay. So Naveen, if you can have that pointer option, you can just point to this. Yeah. So on the left, you can see the -270-degree corner and 90-degree corner. So the problem with 90-degree corner is actually corners will be eroded, and if we look at the 270-degree corner, okay, we will have incomplete removal of the material. Okay, so in either case, we have some etching issues during the fabrication process. But at a certain instance, we can't avoid these corners also. So what we can do is, in the present scenario, even if you can't avoid these 90-degree or 270-degree corners, what you can do is to overcome those effects. Okay, in one side you can see it is etching more, and the other side you can see it is the incomplete removal of the thing. So what you can do is make use of equal number of corners. Okay, so equal number of 90-degree and 270-degree corners. If you have one corner with 90-degree, okay, where etching is not done completely, complete removal of material is not done, and if you have one more 270 corner, okay, with more material is etched out, then you can match that thing, okay. So in that way you can have a better matching. So these things you have to take care in the layout itself. So when you move to the next slide, yeah. So this is basically the cross section of a MOS capacitor layout, okay, mean a MOS cap. So I'm showing a single section. You can see only you have one gate, polysilicon gate. Okay. So what we are I'm trying to show is how what are the parasitics associated with. So since we are
ये तो कल की लिस्ट में आ गई तो कल की लिस्ट है तो पुष्पा मैंने कल देखी थी लिस्ट पुष्पा ये सही है
hello, am I audible now?
Yes, Sidhu, you are audible.
ये पीछे वो बूंद ने वो किया था ना प्रोग्राम
Participants, please keep your mics mute, please.
So always recommended to go with L minimum, so that the resistance associated with the polysilicon gate, because you already know the polysilicon is a high resistive or high material, so we always better to go with the L minimum there. Okay, so minimize the gate series resistance and channel resistance. That is what recommended. Okay, when you go for a MOS capacitor, try to avoid those parasites. Minimize your channel resistance and also the gate series. So what are the gate series resistance is what I have shown in the figure. So if you move to the next slide, you can see the layout of a MOS capacitor. Okay. So as I said, the same thing. Okay, and minimize the gate series resistance and channel resistance. Okay, so what can be done to minimize those things? That is what I have shown here. You can use multi-finger structure. Okay, multi-finger structure basically keeps your series channel resistance, series polysilicon resistance in parallel, so the effective resistance, okay, will get reduced actually. Okay, so this can be an option when you go for a MOS capacitor layer, and if you want to incorporate a huge capacitor in the range of some 10 pico or more than that, you can go for a multi-finger capacitor rather than going for a single finger. Okay. If we move to the next slide, yeah, here actually I'm showing the layout of a matched capacitor. Okay, how we can do a matched capacitor layout basically. Okay. So this is basically a common centroid structure. So what is the common centroid point? If you look into the common any shape you take, the common centroid point is in physics. The definition is like it is the point where the center of gravity, okay, that's situated. So if you look at if you take a rectangle or a square, the common centroid point will be the where your diagonals coincide, right? Or if you take a circle, if you draw the diameter, okay, and then you can see the point where it coincides or meets, you can see that is a common centroid. Okay, that is where your center of gravity is situated. So if you look into a common centroid structure, how we can do a common centroid layout, I will be elaborating it for a MOSFET. So also here we have used a common centroid structure for better matching, and also the dummy capacitors are also needed. Okay, as I said in the beginning, for the resistors and MOSFET to create the same environment for both C1 and C2. So you can see here, you can see many C1 and C2s are instantiated here. Okay, and I'm also saying that okay, we need to match between C1 and C2, but why this much capacitors are in picture? So this is basically we have taken the advantage of unit matching. So suppose what happens is, suppose you have a C1, let's say some capacitor value of 1 picofarad, okay, and you have C2, okay, of same value, 1 picofarad, or let's, for the ease of calculation, let's take 10 picofarad each for C1 and C2. So what we will do is, if you want to match them and if you want to do a common centroid structure, what we will do is you will further make unit capacitors of lesser values. So suppose for 10 picofarad C1, we will take 1 picofarad, okay, as a unit capacitor, and will instantiate, okay, 10 such capacitors in parallel. So what happens, the entire parallel combination of 10 small unit capacitors, each with the value of 1 picofarad, that will give you total of 10 picofarad, right? So what we have done here is we have actually 16 capacitors, okay, in total, that is C1 and C2. So we have made C1 divided C1 into 8 unit capacitors and C2 also into 8 unit capacitors. Okay, that enables you to do a common centroid structure. Also, you can go for a better aspect ratio in your layout. Okay, rather than if you go and instantiate a 10 picofarad directly, it will be in huge size and it will be tough to get the aspect ratio. Okay, so always if you do a layout, we'll be looking for a better aspect ratio. When I say better aspect ratio, the L into W values I mean. Okay, so the area. So always we look for a rectangle kind of thing. From the top view, we'll be looking for a rectangle kind of thing or a square shape basically. Okay, or in worst cases we'll be going for like linear ones. Okay, so always we will try to have a better aspect ratio on your. So in that case, it is better to instantiate unit capacitor, divide your huge capacitor into unit capacitors, and make use of your common-centered structure, dummy capacitors, and interdigitization. Okay, for a better matching between C and F. So that is what I have shown here. We will be showing the same thing in the op-amp layout for the compensation capacitor also. If we move to the next slide, okay, we are actually starting with the layout of a MOS transistor, which is more significant in today's topic. So what are the criteria for a MOS transistor layout? So one criteria is minimize the gate series resistance, that is mainly contributed by your polysilicon, and minimize the source or drain resistance. Okay, that's channel resistance. Minimize source to substrate or drain to substrate parasitic capacitance also. Okay, so these are the main parasitics, okay, which arises. So all the source to substrate or drain to substrate, that is what you see as your CDB, okay, CSB, CGB, all those values. Okay, that are the source to bulk or drain to bulk. We can put it in that way also. Also, you have capacity in between metal to metal, and also you can see gate to source. You have parasitic capacitance. Okay, you have gate to drain parasitic capacitance. Okay? So whenever two layers come in parallel and you have a dielectric in between, you have capacity. But these are the major contributors. Okay? So try to minimize these values. So that are the first main criteria for a MOS transistor layer. Okay, so if you move to the next slide, I have some statistics for you. I have taken the reference from 0.180 micrometer, that's 180 nanometer. Okay, large. So here, there you can see it will be a large gate series resistance is present. That ranges between the sheet channel resistance ranges between 7.8 to 8 plus or minus 2.5 ohm per square meter, okay, micrometer square. Okay, for 180 nanometer process. Okay, large distributed resistance. So if you look at, you can see what is distributed and the series drain resistance. That is what I have shown. Okay, in the figure on the right side. Then you have non-uniform source drain voltages. Okay, also the non-uniform current flow is also there. Okay, so these all things, okay, actually contributes non-linearity to your MOSFET. These all things actually makes your MOSFET more non-linear. Okay? So how to overcome those things? That is what we are going to discuss in the coming slide. So if we move to the next slide. I already told the main criteria. One of the main criteria was minimize the source or drain resistances, right? So how we can use multiple contacts at source and drain. Okay? So always it is recommended if you make a connection between metal 1 to 2, or if you are moving from metal 1 to 2, okay. So it is always recommended to put more wires, and also also if you want to attach contacts on a metal, it is always recommended to attach more contacts so that your design or the layout becomes more porous, okay, to the signals. Okay, then better the contact and source or drain, okay, it gives you higher reliability, okay, and smaller contact resistance. Okay, smaller source drain resistance are also recommended. Also, contacts are not allowed on the gate above the channel because high temperature is required to form the contacts, and that may destroy your thin gate oxide. That is the oxide layer you can see on top of the gate. So it is not allowed. Okay, so it is always recommended not to use contacts, okay, on the gate above the channel. So if you move to the next slide. So these are the basic layouts for the MOSFETs. You can see poly contacts at both ends. Then also to reduce the gate series resistance, we can use folded structures. Okay. So as you have seen, the same thing for the MOS capacitors. In order to reduce the poly series resistance, we used multi-finger MOSFETs there. So the same thing can be used here. So that those layouts I have shown here. So if you move to the next slide. So these are the basic techniques, okay, to minimize the source or substrate or drain to substrate parasitic capacity. Okay, so we have discussed how to reduce the parasitic resistance, basically for the series polysilicon resistance, also the channel resistance. Okay, so now we are discussing how we can reduce the source to substrate or drain to substrate parasitic capacity. So basically, for 180 nanometer technology, your source and drain will be in metal one. Okay, so metal one to your substrate, there will be a capacitance, obviously. Okay, so how we can reduce that? One of those techniques is use shared terminals. So for you can use shared source or drains. Okay, that also reduces the silicon area. So suppose you have two source terminals. Okay, here I have shown in the first figure. Navin, if you can bring the pointer. Yeah. Yeah, so here what I have done is you can see M1, M2, M3, and M4. Okay, that's so whatever the M1, M2, M3, M4, that are four transistors here, which actually share their drain or source terminal. So what happened here in the polygon shape, which is noted as M1 is the polygate. I have noted in the figure it as a polygate. So M1, M3, M2, and M1, we have four polygates of four different transistors. So what happened here is, if you are considering the left side of M1, that metal as source, okay, there you can see the contacts also. And on the right, you can see, if you are denoting it as a drain, that is the right of the M1, right? No, the right of the M1. Yeah, that is a drain. And you can see the drain of M2 is also shared with M1. Okay, obviously M2 will be flipped to make those arrangements. Okay, so when it can be shared, you can't share in all the time. If both are actually carrying the same signals, okay, or both are having the same polarity, you can share. Otherwise, you can't share. Okay, and that is the other thing you keep in mind. Okay, it is not always recommended that you whatever the M1, M2 you have, you can always share. No, it is not the scenario every time. If you have same signal sources passing through your source or drain, you can share them. So that actually helps minimizes your source to or drain to substrate capacity, because you are saving one of your metal area for your source or drain. Okay, since you are sharing, you can make the connections with only one source or drain metal. Okay, if it was not the case, you have to use separate drain metals for your drains for each. So we are actually reducing the drain to substrate or source to substrate parasitic capacitance here. Also, you are reducing your area. That is also another advantage. So if you move to the next figure, so we are now we are coming back to your match your op-amp layout, whatever you have seen yesterday. So it is not a 7-pack op-amp. We are just I'm showing you differential pair, that the first stage of a 7-pack op-amp. So all the circuit perspectives you already defined. So which are the elements that to be matched here? That is what my first question. So which are the critical devices here that has to be matched? Okay. So you can see the first figure and the second figure. It is a development of the first figure. Like we have used current mirror to bias your tail transistor, and also to bias your PMOS load on the top, that is M3 and M4. So to bias M3 and M4, and also the tail transistor. Sorry, I have used the same names here. So for the tail and for the load PMOSs, we have used current mirrors to bias them. So that is what you can see in the second figure. Okay. So which are the critical devices that has to be matched here? That is what, as a layout engineer, you should think from the schematic list. So as I already told, matching becomes a prime concern when it comes to the input differential input pair of devices, and also so there actually you need to match your you require a voltage matching there, and also when it comes to a current mirror there, current matching becomes significant, right? Because you are copying a IRF to another device. So what are the drain current in your current copier, that should be same in the output. So here actually the devices which has to be matched, we have to identify first. So obviously here it is M1 and M2 from the schematic sorry, MOSFET numbers from the schematic, and also the current mirrors here. Okay? What are the current mirrors you can see here? So these things has to be matched, right? Okay? So you have, as a layout designer, you have to identify, okay, which are the critical devices which has to be matched. Okay. So it is better to match. So if you see the differential pair here, it is always recommended to match your M3 and M4. Okay, but whatever the criteria we have seen till now for matching your MOSFETs, or we say to take the example of your resistor or passives, whatever. Okay, we have given you many criteria, but as a layout engineer, okay, it is not possible to realize or okay or satisfy all your design or matching criteria, okay, in a single layout. So then what is possible is it will depend upon your application, whether it's a high speed or a PMICs or a RF circuit. Okay, what depending upon the application, we may have to sacrifice something. Okay, so if you are asked, if you are given a differential pair, differential circuit, okay, like this, and asked which are the critical ones are obviously M1, M2, and whatever the current mirror circuits here. Okay, other things are can be, if possible, if you can match the other devices also, that is M3 and M4, then it is always good. Okay, but critical ones are this. Okay, so we always give preference to this one, and if the other things also can be matched, obviously fine. So if you move to the next slide, yeah, I have given the orientation of transistors. So okay, so this is an important criteria, okay, as for your active devices or MOSFETs, and also it is an important criteria in your passive devices also. So as already mentioned for the resistive resistor part, that orientation is a prime criteria. So here also orientation matters a lot. So always recommended to go with one orientation in your entire layout. Suppose for the in this last slide you have the define, right? So for that one, if you are using your input transistors, okay, you are using your input and that is M1 and M2. Okay, so if M1 you are going for a vertical orientation, okay, then for M2 also you should go for a vertical orientation, or you can go for a horizontal orientation, both. But you can't, rather than that, you can't go for M1 as horizontal and the other one as vertical. That is not good for matching. That's what I have shown in the first figure. Okay, you can see the tick mark there. In the first set of MOSFETs, okay, first pair of MOSFET, I have used vertical, okay, matching vertical orientation, and in the second set, one is in vertical and the other one is horizontal. That is not recommended. Okay. Okay. So in the bottom figure, you can see the first one is in a horizontal orientation, other one is in vertical orientation. That is false. That is okay. Okay. So in one single layout, it is recommended to keep that same orientation for all the MOSFETs. Okay. So if we move to the next slide. Move to the next slide. I am giving you some scenarios, okay, where matching becomes critical. As you can see, in the first thing, different options I'm giving. Okay, then the first figure you can see M1 and M2 obviously has to be matched. So you can use dummies. Okay, so you can use dummies. Okay, on the left and right of your devices. So my question is, for M1, I have on the right, I have M2. Okay, so obviously, if M1 looks onto his left side, okay, onto the left, we should also see, if you want to have the identical environment on both sides, that is on right and left of your M1, okay, you should have the dummy device as M2, right? Because on his right he has M2, so onto the left also he has to have M2. Okay. So what we are doing is we are attaching a dummy device here. So Navin, if you can bring the pointer to the first figure, you can see M1 and M2. Okay, on to the right of M1 you have M2 there, and also on to the left of M1 you don't have anything actually. But what we have done is, to in order to keep the identical surroundings for M1, we have added a dummy, okay, which exactly resembles as your M2. Okay, but that doesn't have any significance to your circuit. What we'll do is, if it is a NMOS, we will short all the devices, all the terminals, that is source, gate, and drain terminals, and we'll short them to ground. Right? So also you can see the same effect on the right side. On the right of M2, you have a on the left of M2, you have M1. Okay. Onto the left of M2, you have M1, and onto the right, we are attaching a dummy which is same as your M1. Okay, so that the identical environment has been taken care of. Okay, now we can see here in this layout, that is in the second scenario, with M2. Okay, you have some wire going through. Okay, that metal I'm showing it as on the right of M2 attached to M2. So when you look at M1, okay, doesn't have any symmetry, right? Because on the other side you have one routing plan, and onto the left you don't have the same thing. So obviously, if M1 and M2 has to be matched, I don't recommend this kind of routing. I'm looking for a more kind of a balanced routing here. So that is what I have done in the third stage. Okay, so two devices has to be matched and has to be in common centroid or interdigitization. All these steps we have done. Also, it is very important to keep balanced routing. Okay, balanced routing plans for M1 and M2. Okay, so as I told earlier, you can't have balanced routing everywhere, because if you go for a routability check, or if you go for a routing plan, okay, you may have routing congestion in your layer. So it is always, we can't go for a balanced routing, but up to maximum extent possible, you do that, so that your transistors are better matched. Okay, if we go to the next slide. Yeah, as I mentioned, matched transistors obviously require elaborated layout technique. So from the beginning itself, I'm saying the word use interdigitization. Okay, so what is interdigitization? Okay, and average. So what happens in interdigitization is it averages the process variation among the transistors. Okay, so we make use of common terminals. Okay, if it is a common terminal drain or whatever, we make use of serpentine kind of structure. That is what you can see. The source terminal is common here in the layout below. Now, if you can bring the pointers, you can see for the source terminal. Okay, we have made use of interdigitization. Okay, so the source terminals, you can see the serpentine. Okay, which looks like a snake, that red pink color layer. So S1 and S2 are interdigitized. So to connect them, I need a metal on the top. That's how it came to a serpentine. Then uneven total drain area between M1 and M2, because M1 and M2 has to be matched, and uneven drain area, okay, on both half of the circuit, that is not desirable for the matching condition. Okay, so also it is desirable to use dummies if needed in order to provide identical environment. So if you move to the next slide, that gives you a detailed view of what is a common centroid. Okay. So this is basically a common centroid layout, what I'm trying to elaborate here. So I have two scenarios here. One is A and one is B. So in both scenarios, A, I have done some arrangements of A1 and A2 and B1, B2, and also in second scenario also I have arranged in different manner. So what is significance of this? That's what I want to say. Okay. So you might have heard about the linear gradient. Okay, that is a graph I have shown in the bottom figure. Okay, so the variation of that linear gradient, okay, that is basically indicates the process variation. Okay, so depending upon where you place the transistor, okay, okay, on your left.
Hello. Hello.
So I think his audio problem.
Navin, am I audible?
Yeah, you're audible now.
Yeah. So in the first figure, you can see A1, A2, B1 and B2. Okay, so what is A1 and A2? So what we are trying to do here is you have we have to match between A and B basically. So what is A1 and A2 is I have used a multiplier of 2 for if suppose A is a MOSFET, A and B is a MOSFET which has to be matched. Let's suppose it's a differential pair of MOSFETs. One is A and one is B, and I have used a multiplier 2 for each MOSFET. So that is how it turns out to be A1 and A2. That is and also B1 and B2. So this has to be matched. Okay, so what can be done is if you look at the common central thing, you can see the linear. I already told that linear gradient varies as you move away. Okay, so what happens here in the first pattern, that is A1, A2, that is both the A1 and A2 are placed together, then you have B1 and B2. So let's actually calculate what is the linear gradient, okay, or the process variation for each one. So as you can see, A1 is more closer to the origin, okay, so that have less process variation, okay. Then A2 has little, okay, more process variation than A1. So the total process variation, okay, that comes to A, okay, that is A1 plus A2. That is what you can see on the equation A on the top. Naveen, can you bring your pointer to the top? The first equation. First equation on the top. Yeah. So in the first arrangement, you can see A1 plus A2, that is the total process variation, okay, to the transistor or MOSFET A, that is A1 plus A2. And if you consider that, now if you look back to the figure, you can see in the first arrangement, B1 and B2. B1 is having, okay, much higher process variation compared to A2, right? You can also correlate to the graph. Okay, that's how I'm saying the values. So B1 has much higher process variation compared to A2. Okay, and also if you look at B2 in the first arrangement, it is having the highest process variation. So if you count the total impact of process variation upon B, that is B1 plus B2, that is obviously much greater than the process variation impact on A1. That is how I wrote it as A1 plus A2, that is the total process variation contribution to A, which is lesser than B. Okay. So what we analyze from this one, that means that this is not matched properly because A1 is having some process variation which is less than B1. So if you want to match them, what do you want to do? Both should experience the similar process variation. Okay, then only it will cancel out if you look into a differential configuration. So what can be done? That is what we have done in the second arrangement B. That is what we call as common centroid arrangement. So what we have done here is, instead of arranging A1, we have kept first, that is the least experiencing least variation. And what we done is the identical pair of A, which we denote as A2, which we kept on the farthest end. Okay. Okay. So A1 has least and A2 has the most higher gradient. Okay. And what we did is the B, the transistor B, also having multiplier B1 and B2, that we kept in the middle. So now if you calculate that linear gradient, okay, that is what we have shown in the second figure, second equation. Okay, you can see A1 plus A2. Okay, A1 plus A2 is, A1 is the least one and A2 is the farthest one. So that actually becomes equal to B1 and B2, right? You can look in the graph also. So in the second arrangement, what we have done is we are able to match the process variations effect to A and B, right? Okay, you can maybe substitute some values and figure it out. Okay, if you are not able to figure out from the graph, okay, you can just substitute the process variations for one A1 as 1, and when he moves to the B1, it can be 2, and the next one can be 3, and if the next one is 4, if you total it out, you can find it will be getting identical values. So in this arrangement, that is what the common centered thing, okay, helps you to, this is how it helps you to match the devices. Okay.
Shijo sir.
Yes, sir.
What is the difference between first three and the next three lines? They are looking same?
No, sir, that is a mistake. I just copied it 2 times. That's why.
Acha, okay. That's a mistake. Acha, one more point. I I think this sequence should be A1, B2, B1, A2, right? No?
Yeah, yeah.
Rather than A1, B1, B2, means B sequence. If you see B sequence, you have arranged it like A1, B1, B2, A2.
Yes,
I
sir.
think
Both
it should
possible. Both are possible. Both are possible.
both. Let us take A1 is a resistance with 1000 ohms. Okay.
Yes, sir.
So A2 will be, let us take a process variation of 10 ohms. Then 1000, 1010, 1020, 1030, right?
Yes.
So if I move B2 to A1, so it is 1000 plus 1000, what I said, 20, 30, 1000 plus 1030, 2030 it will be.
Yes.
And then this will be 10 plus, yes, I think, but then if I exchange, if I take B1, it will not be same, no? 1000,
No,
yes, huh?
it will depend upon the values you choose, sir. Because logically, if you look at it, no, rather than putting it as a value, A1 is something in the first arrangement. Obviously, A1 and A2 are the ones with the least.
Yes, that's what. So what I think is this sequence should be least variation together, has to be there. Means A1 has a least variation and the B2 has the maximum variation. So together when you combine, that is going to be the some, I think so. Okay.
Because if you look at the introduced patterns, actually both are recommended, sir. If you look at Alan Hastings,
Acha.
both are recommended. Basically, you can go for A B B A, or you can go for A B A B. That is also both are recommended. Actually.
Okay, take it. Fine. Okay, sir.
Yeah. So we move to the next slide now. Yeah. So this is, I'm looking from a different aspect, right from looking into that center of gravity. Okay, for a common centroid point. So that is the midpoint. You can see that is the common centroid point. So you can here actually, as Sir said, I have arranged in this way: A B kind of. Okay, that's yeah. So here also it is actually we have M1 of 8 transistors, M1 of multiplier 8, okay, and M2 of multiplier 8 again. Okay. So the location also matters basically. Okay, so from that midpoint, okay, all the transistors should be on identical location. So you can just you can go for the coordinates and you can identify those things. Okay, so that is another way of looking at the common center. Okay. So if you move to the next slide. Okay, so this is a interdigitization technique. Okay, that is placing alternate components as we have discussed before. Okay, so here also we can see we are actually interdigitization between A and B. Okay, each with a multiplier 4. So this also can be recommended. Instead of A B B A, you can also go for A B A B. That is another variation of a pattern here. So that is placing the alternate command. That is what we call as interdigitization technique. Okay. So if you move to the next slide. Yeah. So I hope the picture is not that clear. So you can see this is again an example for a common centroid layout. So what I want to clarify here is, okay, for a common centroid layout, we can look from the common centroid point. We can say, let's say, let's consider this as a rectangle. So at the midpoint of the diagonal where it meets, okay, that can be the midpoint. That is one of the common centroid point. It can be in the middle almost. Okay, yeah, somewhere there. So what you can say is, suppose you want to do a common centroid layout for a differential amplifier. Okay, so input devices M1 and M2. So what happens is, as I said, you can place the transistors in interdigitized pattern and also on the common centroid way. Then the next thing what matters is the balance routing. Okay, so suppose for M1, so Navin, can you quickly go to that schematic one? Op-amp schematic in the slide itself, 2-3 slides back, I guess. Yeah, yeah. So if you look in detail into this slide, you can see if you want to match M1 and M2, you can just refer to the first figure on the left. If you want to M1 and M2, it's okay. We have arranged it in common central view. Everything is fine. Now there is a significance of balance routing also in when it comes to matching. So you can see the input wires. So that is for gate terminals. Okay, what are wire source input source to your gate terminal? That wire should be identical. Okay. Also, you can see the output from where we are taking the output, differential output. So if you can, Naveen, you can point to those wires from the drain. Yeah. So you can see from M1, okay, the drain terminal goes to Vout and that connects to the source terminal of M3. So you can see the similar parallel arrangement on the right side also. That is from the M2 drain, it is going to M4 basically. So when you go for a matched layout, it is always recommended a balanced routing. So those who is going in parallel, that is the drain terminal, wire, which is going from M7 drain to the drain terminal of M3, those length and width dot also should be matched to the one on the right side. That is the wire going from the drain terminal of M2 to the drain terminal of M4. That is a PMOS device. No, in the same figure, now in the same figure, left and right side. From M1 to M3 and M2 to M4. Those the wires which we realize for the connection between the drains and the output, that also should be matched in terms of length and also because why it should be matched means we are actually doing all the analysis, taking it for granted that it is a differential signal and it is an identical pair of devices on both halves. So the signals passing through them also should be identical. Then only the perfect rejection of common mode noise will happen in a different circuit. That is what all the aim is. So in order to have that condition satisfied, it is always recommended to go for a match balance routing, okay, for your matched pair of devices, that is M1 and M2. Okay, so coming back to your slide 35 now. Yeah. So I don't know whether is it visible. I hope now is it visible, right? The drain and terminals. Yeah.
Yes,
so
it is visible.
So if you can see the this thing, okay, all the drain connection, that is D1 and D2 from the common centroid point D1 and D2. Okay, you have two drain terminals on the left and right side. Okay, that is how I made the balance routing here. Okay, so half of the drain, okay, drain terminals I pushed on to the right side of my common centroid point, and half of the drain terminals I pushed into the right of my common centroid terminal. So you can see from the midpoint, you can see D1 and D2 to the left, okay, and also D1 and D1, that is a midpoint, and to the right of the common centroid point, you can see, as Naveen pointed out, D2 and D1 to the right also. So you have two drain terminals to the right of your common centroid point and also to the left. In the same way, I have arranged the source terminals also. Okay. So that is so we are also looking for a balanced routing also. So you can do the floor planning first for whatever the matched pair of devices. You can do the floor plan first. Then you should look for when you come for the routing plan. These are the critical nets. Identify the critical nets, okay, from the schematic which are to be matched. Then do a balanced routing there, so that you have identical conditions on your right and left side of your common centroid point. So actually speaking, it should be a mirror, okay, of your left side and right side should look like a mirror image of both. Okay, the left side should look like a mirror image of the right or vice versa. So that is what we are actually looking for. Okay, but it is obviously as most of the professors almost have gone through the scenario. It is not possible always to achieve all this balance routing, common centroid, interdigitization, all the criteria, okay, in the same layout. But up to the what extent is it possible do that? That is what recommended. Okay. Because as you go down the technologies, it is very difficult to realize things. So up to what extent it is possible, do till that. That is what. So let's move to the summary. So as a summary, can tell always use large area to reduce that random error, but it is not always recommended to use large area because area is constrained, okay, in many cases. Okay, but if you look at the defense industry or something like that, okay, they are actually they are not looking for a less area or something. So they are happy with still working. You can see they will be still working with on upper technologies like 230 or maybe beyond that. Okay, they are still in that olden era. They have not come to 5 nanometer and all. So it is basically the electronic gadgets, we can say, that came to this 5 nanometer and all. So if you look at the defense industry and all, they're still working with higher technology. So there we can use the large area to reduce these random errors. Okay? And also recommended to go for a common centroid layout. Okay, okay, to reduce that linear gradient errors. Also, you can use unit element arrays because when you have a huge capacitance, instead of instantiating a 2 pico or a 10 pico capacitance directly into your schematic, you can go make it as a divide it into a smaller unit capacitance of lesser area, and you can complete the layout with a better interdigitization and common central time. Okay. And always go for use of symmetry is always recommended, and that is basically the orientation we use. Going with a vertical orientation, always recommended to go with vertical orientation. Okay. Okay, and you also use dummy devices wherever possible. Okay, for a better similar vicinity, or you can say to provide similar environments. Okay. Also, it is recommended to put guard rings, especially for the input pair of transistors. Okay, that is for a better isolation, so that the signal variations, okay, especially when it comes to PSRR of an op amp and all, okay, whatever the variations apply your supply and all, that should not affect, okay, your circuit. Okay, okay. So PSRR becomes a main concern in your op amp or in your LDO and all. When it comes to LD and all, PSRR becomes a prime concern there. So for there, actually, it is always recommended to have guard rings, which will which will isolate the supply signals from the other elements in your circuit, okay, which provides separate VDD and ground rails for that. So it is always recommended guard rings for isolation. So these are the summary things. So we can just quickly go to the, we are already running late in the clock. We'll just quickly have a look into the op amp layout. Okay. So the circuit part of it we have designed yesterday. I hope if you remember, we have designed it for a power consumption of 50 microwatts. Okay. For a drain current for the first stage of 12.5 through each input devices. Okay. And also you have a second stage, basically 7-pack op amp, and the final stage we have again a class A B push sorry again a class A stage, okay, as a PMOS as the input device, okay, with a drain current consumption of 125 microamp. So we have designed it for a gain greater than 60 dB, looking for a maximum bandwidth, unity gain bandwidth. So we choose L minimum. So we have looked at the circuit perspective. Also, we have looked into the frequency compensation part of it. Okay, we have choose the compensation capacity and also RZ value for as a nulling zero resistance. So for that one, we have done a layout. Okay, we have, so we'll quickly look into the layout, how the floor planning can be done in the available time. So here, before going to the layout, okay, as a layout engineer, I recommend you to identify the critical transistors, or which all things has to be matched. I have not shown any current mirror for biasing here. Okay, so you can see the input devices, obviously the M1 and M2. Okay, you see in the schematic that has to be matched, and also the PMOS load, that is again a current mirror load, that also has to be matched, because whatever the current through PM1, you are copying to PM. So those, that also has to be matched. So we'll quickly look into the layout. Okay. So Naveen, if you can. Yeah. So this is the layout for the complete layout for the 7-pack op amp, including the compensation capacitor and resistance. Okay. So I will tell you a few points what we discussed in the during the slides, okay, in the theoretical session for the matching techniques and all. I have used few of them here. So let me tell you those things, because I don't have much number of transistors for my input device, because all of them are with multiplier 1. So I don't have A1, A2, A3 and B1, B2, B3 like that. So matching can be done up to a small extent here, because I am not able to show the interdigitized pattern and all, because I have less number of transistors to be matched. So if you look into the input pair of devices, so Naveen, if you can, yeah. So you can see, yeah, can you just zoom to that input pair of devices, Naveen? Yeah, fine. So if you point that one, we can see two pair of transistors at the middle, that is NM0 and NM1. Okay, these are the input pair of transistors. Since it is a multiplier 1, I can't go for a multiplier 2, because we are already in 0.625 micrometer, the device width I'm saying. So the minimum allowable width is 400 nano, that is 0.4 basically. So I'm not, I can't go for a multiplier 2 here, so I have to go with multiplier 1 itself. There are only two devices to be matched. Then you can see I have added a dummy also onto the left. So Naveen, if you can point, yeah, there you can see a dummy to provide the identical conditions for NM1. But because if you look at NM0 to the right, you can see NM1. No, in the middle now. In the middle. Yeah, to the right you can see NM1. So to the left also I have to see the same thing. So I have added a dummy which almost resembles the as your neighbor. Okay, so that is what I have done there. Also on the right side also you can see a dummy in the name of NM0 there. Okay, so I have attached two dummies here. Okay, and also if you look at the you can see a guard ring also on the outside. For the I have provided guard ring also there. I mean, if you can point to that guard ring, so it's a, yeah, you can see a guard ring also. So if you then go for the properties, I think, so you can see the guarding also there for a better isolation. And I have, so what happens here is for the NMOS devices, it has separate, it has isolated, we have isolated from the other devices. Okay. Then if you can look at the top, that is the PMOS load. Okay. I mean, can you go to the PMOS? Yeah. So here also you can see in the middle, we have 4 transistors. Okay. So since it is having double the almost 4 times the width of NMOS, I was able to make use of multiplier 2 for each devices. So I have 4 devices to be matched. Okay, and I also have used dummies. Okay, which is surrounding all those things. But you can see there is a limitation. As I said, we can't put dummies as everywhere, because that will end up with a routing congestion. So in the bottom, you can see I have not added any dummies, but onto the left and right, okay, onto the left end column and the top row, you can see these are all dummies basically. Okay. So wherever it is possible, you use it. That's all. Also, in order to have a better aspect ratio, I have filled the vacant spaces also with dummies. So now the next thing was the capacitor. Okay, so Naveen, can you fit to the screen? F. Yeah. Can you zoom that capacitor? Yeah. Thank you. So here what you can see is, if you remember, we used actually compensation capacitor, okay, of 2.2 picofarads basically. So if you instantiate a 2.2 picofarad, okay, that will be a huge value basically. Okay, so what I have done is, in order to have a better aspect ratio and in order to have a better matching, what I have done is I have taken a unit capacitor, okay, and made 12 of such devices. Okay, so connected all of them in parallel, so that, okay, the total capacitance of that 12 unit capacitance will sum up to 2.2 pico. So if you go to the schematic now, if you can go to the schematic, you can set the unit capacitance Okay, you can decide upon the values there. So yeah, no, capacitor, no. NMOS 3-terminal cap is there onto the left of, yeah. So if you go for the properties there, Naveen, can you go to the properties? Yeah. If you go for the properties, you can see there the total capacitance. Naveen, can you move to the total capacitance? Yeah, it is 2.19. So almost equal to 2.2 picofarad. And if you come back down, you can see I have used a multiplier of 12. Okay, multiplier of 12. So I have made the 2.2 into 12 unit capacitance. Okay, each with value of 1. That is what you can see on the first row, first column. Yeah, 183 femto. Okay, so that gives me, if you connect them in parallel, that gives me a total of 2.2, almost equal to 2.2 picofarad. Okay, that is how I realize the unit capacitance there. So this is one approach, because obviously if you use a compensation capacitor, okay, the area may come before you close money. Yeah, you can see the area here. Okay, each capacitance is of 4 into 4 U basically. So if we use 12 of such types, total will be actually 48 into 48 U. So that much big area the capacitor will consume. Okay, so obviously it will be a huge area compared to your MOSFET. So if you look back into your layout, yeah, you can see the area consumed by capacitor is always large. So it is always recommended to use, if possible, use capacitor which will give you large resistance. So for that, you can look into the foundry files and you can identify which capacitor is having or possessing large unit capacitance per area, large capacitance per area, then you can choose that. So that you can, if you realize a huge value of capacitor in the range of picofarads, okay, you can realize it with a less area. Okay. So that is one thing I want to tell you. Also, I have given, Naveen, can you press there? Also, I have given separate VDD and VSS rails on the top so that connections can be, the routing congestion can be avoided. Okay. Okay. Then one more thing I want to show is, Naveen, can you come to the input pair of devices? Yeah. Can you double click on that? Yeah. Yes, Naveen. So here you can see this is a module generator window basically. Okay. I don't know, in all the campuses, do we have license for the module generating that is the short form. So I think in the last session, few of the participants asked whether we can do a automatic routing or automatic placement, okay, in your layout. Yes, that is possible. What you have to do is you can check in your license in your campuses. I don't know whether the previous versions of license or the UG and PG bundle have these features, but obviously research bundle have these features. You have a option for module generator. Okay, there actually the tool is actually helps you to create balance routing. Okay, you can generate the patterns, you can go for automatic placement and routing, all those things. But as a analog layout engineer, okay, these tool features actually will help you to get a maybe primary or a rough idea about the floor plan or the routing plan, but this will not be this will not be a optimized layout as a whole. So it is always, you can see the industry practice is always no need to is to go by the conventional way. Okay, in most of the industry, you can see they will not be using any advanced automated stuff for the analog layout or the custom IC layout, because that will not be an automated layout. Okay, because you can see if you come out of this window, I mean, can you come out of this window? You can have a save button on the left side. Yeah. Did you close it? Yeah. Yeah. So I have made use of that guardrails from that one limitation of this module generator, I can say automated tool. What I want to point out is, see, I have generated a guard ring here. Okay. But you can see between the guard ring and the inside guard ring and the wires, that is net 27, net 25, you can see there is a huge space. Okay, so it can be still optimized. Okay, so if you draw by your in the conventional way, that is from each layer by layer. Okay, maybe you can reduce those areas and all. Okay, so if you go with a automated thing, that is automatic placement and routing. Okay, that will actually will not give you a optimized layout, but always it will give you an idea, okay, about the floor plan. Also you can get a idea on the aspect ratio. Okay, if you press F, nothing. Yeah, so these are the few things I want to specify here. Also you can measure what is the area consumed for this layer. So Naveen, if you can measure, okay.
So yes, yes, Sujat. So you can go to tools, and there you can go for area and the density calculator. Okay, so it gives, so you are measuring the area for entire cell view, right, and all the objects. Okay, so enable those things, and if you select OK, then you can get the total area occupied by your layer. Okay, so everything is in micrometer square. Okay, because cadence follows micron-based design rules. So everything is in micrometer square. The total area is in micrometer square, and here you can see the density of your layer. Or otherwise, you can make use of rulers, okay, and use the basic formula to calculate the area for a triangle. Okay,
Yeah.
so what you can do is you can use the ruler and top to bottom, you have to measure, and then from left to right. Okay, so multiply these things, and so 71.64 into 35.7 will give you the area total.
And one more thing I want to specify here, like I think I hope you most of the campuses are working on the research project, so they'll be, if you're looking for a tapeout, obviously you have to do the layout. So there is a thing called off-grid errors. Usually the layout engineers come across while doing the design. I don't know. So what happens is for each foundry, okay, if you press E, the short key is E. If you press E, you will get the grid settings basically. Okay, so you can set the grid settings here. You have a major spacing, minor spacing, then X snap, that is minor spacing, and you have Y snap area. So for the GPDK, this is the default values. But if you are working with some other like foundry files, maybe it can be UMC, TSMC, or whatever the foundry, you have to look into their foundry files, and you should look for the manufacturing grid specification. Okay, so accordingly, you have to specify the values here. So otherwise what happens is, if you are not going with the manufacturing grid specifications, okay, whatever given in your foundry files, okay, maybe you'll not be able to type out the design. So you always recommended to go with the manufacturing grid, okay, because in that grid settings, okay, that is recommended. So otherwise you will end up in off-grid errors. And so usually we used to get queries on this off-grid error things, and always recommended to go with the manufacturing grid. Okay, so we'll quickly go to the extraction of this file. Okay, so we can just extract the parasites quickly. So LBS and DRC we have already shown in the previous, and the same step applies here also. We quickly go for an extraction. We are already running late. Yeah, you can watch the log file. Okay, so you can see what are the things extracted here in the log file. So you can see it has extracted a parasitic capacitor and resistor. And the layout, if you go, okay, you have a AV extracted view. Okay. You can zoom to a portion and you can find this SPI capacitor, resistors, everything extracted. Okay. you plus shift F, you can see capacitor 6. So since it is a small 7-pack op-amp is relatively, it is not a complex design, it's a small design. So these parasitics may not have much effect into your schematic. If you really want to look into a real effect of these parasitics, maybe if you go for a more complex design such as ADC or something like that, okay. So there you can find the defects of this main impact of this parasitics, okay, which comes into it. Also, when you go to the Naveen, can you quickly show that QRC run form?
Yeah.
So since we are working on 180 nanometer here, no, this is not that QRC run form, like from the layout window. Yeah, since we are on 180 nanometer, we just extracted RC values. We have also options to extract RC and L also in that, and RCL, okay. RNCK is also there. So when you go down the technology, okay, if you go down to 5 nanometer of FinFET and all, these things actually, feature inductance and all will comes into picture. At that time, it is always recommended to go with RLC extraction. Okay. Here it is not that significant when it comes to 180 nanometer. That's because we are also it is not that, it's not that shrink compared to the lower technology. So we'll quickly run one post layout simulation. Okay. So yesterday we got a phase margin around 80 dB. Okay. And we got a gain margin of around 80 degrees phase margin and gain margin of around 56 dB we got yesterday. And also we had a loop gain of around 56 dB. So we'll cross check, okay, after the post layout simulation. So can you open the config view now?
Yeah. So if you have a doubt as of whether the parasitic components are imported into your schematic or not, okay, just you can open your test circuit, okay, after creating a config view, okay, and just open this symbol, okay, in a new window, so you can see. So this was your AV and AV extracted view, right? And you had all your parasitic components, so they are imported to your schematic, okay. And now you can open your ADEL window, okay, load the state that you have already saved, okay, and you can run the simulation, okay. You can run the simulation, and you can go to results and go for the main form, okay. We can go for the summary, okay. So
Naveen, am I audible?
yes, you are audible, Sujit.
So can you show the stability summary? Yeah.
Yeah, just a second.
So the stability summary you can see. Naveen, can you just read it to me?
Yeah.
You can plot the loop gain on.
Yes, Sujit, just a second. This is the gate, right? ST,
No, the down one.
STP analysis. Okay. Not getting.
Something wrong there? Okay, you can just cross check on that. Yeah.
Just a second.
Sir, online. Hello.
Hello.
Am I audible, sir?
Yes, you're audible, Sujay.
Yeah. Now you can cross check that. Meanwhile, we are open for queries also because already we are late by 15 minutes. So feel free to unmute yourself and you can ask the queries.
We are getting it now, Sujay.
Yeah, yeah. Can you just read it out?
So yes, stability summary. We are getting the phase margin as 79.2 degrees at a frequency of 7.32 hertz, and gain margin 52.45 dB at a frequency of 298 hertz. Okay, and loop gain also. Let me pull up it. So this is the loop gain.
And split it and measure.
Yeah.
Three dB, right?
Yeah.
We have a slightly reduced value also on the bandwidth also, but there is no huge significant change as I told. This is simple design, so it may not have much impact because we already have a large load capacity of 10 peak. So as you can see, whatever the capacity, parasitic capacitance you extract will be in hectofarads, and so that may not make a much impact. But if you look for a more complex like designs like a PLL or a ADC kind of, you can find the difference. So Navin, can you quickly go back to the slide?
Yeah.
Yeah, next slide. Next slide, next slide. Yeah. So I have few references for you if you are reading just on layout also. For the students, it will be helpful. So the first book is The Art of Analog Layout. You must be familiar with this. It's by Alan Hastings, okay, known as the Bible of Layout. You can find all the matching techniques, process of mismatch, okay, all those things whatever we discussed today, okay, they have this, okay, defined it in detail, okay, and also you can find a glimpse on analog layout also on design of analog CMOS integrated circuits from Belsa Resavi also, but the book I refer is the first one. I don't know whether it's a PDF available on the internet, but you can find the scanned copies may be available. Only international editions are available, I guess. So you can just show those things.
Sir, it is available in academic colleges. Institutions, it is there.
Okay, okay, fine.
Yeah, the art of analog layout is there.
Yeah, yeah. So it's a very good book to refer basically.
Yeah, yeah.
Yes, yes. Sir, we are open for queries. Okay. So meanwhile, we will just show that slow corner analysis in the ADE window. So Navin, can you just set up that? can you open that NMOS characterization? So queries, you can feel free to unmute yourself and ask.
Anybody has any query?
Launch the ADX. Navin, any query on the chat box? Please check. I'm not able to view my chat box.
No, it's not there.
Yes, sir. Unfortunately, I'm giving the session from a hospital, so I'm not able to.
Oh.
Okay, I have a medical emergency, so I just got admitted here. So, yeah, so one of the participants actually requested how to do the corner analysis, basically for the slow and fast corners. So Naveen, you can go to data. We will showcase it for the NMOS characterization, what we have done, that we have done for nominal corner. Okay. So if you look at the corner setup here, Naveen, can you move the pointer there?
Pointer option is not there in Linux CJ.
Okay.
Just I have the mouse pointer.
Okay. So you can look at the mouse pointer. We have corners available. Okay. So in that one, so if you double click on that corner, can you double click on that corner? Yeah. So you can see slow, fast, all the corners are available. So if you come down, click to add corner, one option is there. Down, yeah, click here. Yeah. So this is the corner setup basically. So on the top, I have defined basically nominal, slow, and fast corners basically. Okay. So you can, on the left, you can see GPDK SES files also. Okay. You can add the model files here, and you can also define the corners here. Maybe you can add one more corner if you want to run for a fast slow also. Maybe on the top, on the top, you have a thermometer kind of add corner. Yeah, you can add corner. Maybe you can define it as slow, fast, SR. Okay. Then we can come down in the model files option. You have to double click there and you have to attach the same corner. In the drop down window, I'm not able to see the drop down.
Yes, even I'm not getting it. I'm not getting it, CJ.
Anyway, we'll run with slow and slow fast. Can you come there?
Yeah, just here.
Yeah. No, in the same setup itself. Same setup. Click to add corner. Yeah. So you can enable the corners here. So it will now run for nominal, slow, and fast corners. Okay, why I'm not getting slow fast corners? Basically, it is depend upon the foundry. If it gives you the model file for those corners, you can run. Okay, that is not the problem with GPDK. So here I'm running for what is available, slow and fast, also with nominal corner. So you can just give OK. So one more thing now, I just want to tell there is, yeah, you have a temperature option here. Okay. As you can see on the left side, after corner, on the table I'm saying now, yeah, you have temperature option also. Okay. So in each corner, what is the temperature range also you can specify there. So, and also you can see design variable. Okay. So if you want to, you can create your own corner. For a nominal corner, suppose you want to run it for the temperature range of -120 to 30 degrees Celsius. Okay. And you want to run it for a supply voltage variation for a 3.3 plus or minus 5%. That range also you can define here. So in terms of design variable, you can actually specify the supply voltage there, and you can also run for a supply voltage variation. So this is how you set up the corner. Okay, I'm not going for temperature variations here because it will take huge time. Okay, so you can click OK. We'll run it for the corners at least to get a idea about the flow, how to set up. So these things, okay, for the process corner analysis, you should come into ADXL window. Okay, that is what recommended. Okay, and also now we'll run a short simulation. So can you go to the global variables menu now? We'll reduce the number of points, otherwise I'll be late. Okay, VG of 1. Okay, fine. What is the VG range? VG range? L is okay. W you can put one value, maybe 5U or something. That will be fine. So that at least we are saving some time. Okay. VD you can change to 1.6. I'm just giving arbitrary values. Okay, I'm running for a less number of points. Okay, now we can run.
Yeah, we need to include, right?
VG, let it be in that range. So you can see in the output setup, we have norm specifications. Okay, min, max, slow, and fast. So these are all their, I think, model file you need to check. Yeah, so this is how we run. Can you quickly check that model file now?
Yeah. Yes.
So you need to go to Spectre state and
Yes.
edit
Yes.
it.
Yes.
Yeah. Any queries we can feel to ask because we are already late. Any queries on the chat box also? Nothing we can tell.
No queries on chat box.
Shijo sir, our transistor saturated.
Because sir, when it comes to layout portions, sir, we can't keep anything. Otherwise, it will
Yeah,
not make sense.
yeah.
So that's what that's AC template definition and all. Without telling the template setup, we can't tell standard cell library design itself. So I think we too tight on this date too. Sir, we are looking for feedbacks also. So,
Yeah.
yeah, I think VDK sir has told like he will try to join, but I think he was not able to join the session.
It's over, no? I think almost done.
Yeah. Open an existing, I mean, open existing view. ADXL will be fine. Okay. Rathod sir, you want to add something
So about sir?
about the session feedback?
Acha, session. No, sessions were excellent. We are waiting that to complete your this thing, no technical aspects.
Okay. There is some. Yeah. Navin, can you give that path there? Yeah. Since I am in hospital, I just send the design files to him. So if there is a change in the path in editing, then that will give you an error. So, yeah. Yes. Yes, Navin. You can just show that values. For slow, fast, we have values.
Taking the yeah. Yeah, we have those.
And we
But
look
still
into
it is
the
taking the
simulation.
same line.
Log window is just log window.
For slow and
Is there any error or it is fine? I'm not able to see.
It is fine. I think it is fine. Just come, no?
Oh.
Fast.
Yeah.
the path.
Yeah. So what it is listing out basically is one for the nominal corner, then slow and fast. Then we have min and max basically. So that is actually telling you out of the simulated values, what is the maximum and minimum you got basically. Yes, ma'am. I mean, if you want, you can create a new one. That is not a problem.
Okay. No issues.
You can close this one, come to the spectra state, check the model files from it. Fine, right?
Yeah.
Launch. You can go for and create new one, new ADXL1, some name you can. You go. Yeah, you can go for corners, add corner. Yeah.
Yeah.
On the top. Yes. Put it as slow, whatever. Can come to the model file region. GPDK.sc. The foundry, right? Foundry. Yeah. Go one step back. Not expect, it isn't found. Analog models. Okay. Yeah, in the section you can choose. Yeah, you have all the listings, slow. Yeah. One more corner you can add.
Okay, right?
You can add one more corner. Maybe. Fast. Yeah, add that section. Yeah, fine. So you can just show that listing. We have other listings also, slow, fast. Now, for the time being, run. Got it, right?
Yes, we have got the values for drain curve.
Okay, fine. Yes.
Hello.
Yeah, am I audible?
Yeah.
Okay. Yes, sir. Yeah, we are done with this.
Hello.
Any queries, please feel free to ask.
Any sir related to standard cell design or related to analog layouts?
Shiju sir, I think this is okay.
Yes, sir. Any queries, sir, on the chat box also? Naveen,
Nothing. No.
Okay, fine.
No queries from the chat box.
Okay.
Yeah.
So thank you very much, Rathod sir, especially for coordinating such a wonderful event, and for all the participants, thanks for your patience. Yeah. So we especially.
So, thank you
Hello,
very
sir.
much. Yes.
Sir, for this slow, fast, it has shown only ID.
Yes, sir.
Can we go for seeing other parameters also?
Yeah, we can show.
Only
For the
it was
time,
not. Okay.
we just shown for ID. You can go for all the parameters. In the
Okay,
output
sir.
setup, you need to add them. That's all.
Okay. Thank you.
Sneha madam?
Yeah. Hello.
Yeah, I guess.
Any other queries?
Sir, I don't think there are any queries now.
Oh, okay.
So thank you, sir. Thank you very much, entire team of Entuple. So I would like to start my thanks from Venugopal sir. And just before 3 days, he had discussed in detail what to be taken, what not to be covered. And I'm really thankful to him because he was not well. He has a lot of family compulsions, and then also he has spared one day for us. So this is a kind of a virtual memento from our side to sir. So please convey my regards to him.
Sure.
And yes, sir. And then the book, which title Madam has asked. So please send me those names.
Sure.
Gray and Mayor, but those titles. So thanks, Venugopal sir. Madam, next. And then, sir, this is a virtual memento for you from side.
Thank you.
You are continuously with us. Thanks a lot. You also had a lot of challenges yesterday, but still you overcame them. and you are saying that you are at the hospital. From there, you are running this presentation. Really great. Thanks a lot. And we will go back and see this recording, and we'll try to do it whenever our campus reopens, because now we have a challenge of accessing the cadence. But whenever we go back to our campus, we will see how to, and we will refer your notes again, and we'll go back and see it. And thanks for your real motivation. Great. Thank you very much, sir. Ma'am, next. And obviously, you are a soldier, I would say now. Next one, madam. Yeah, madam. What happened? Yeah, madam, you are not able to click or what? There is a virtual momentum for Naveen. I'm waiting for madam. Madam is not able to click or something like that.
Connectivity.
Some connectivity issue.
Yes, sir, yes.
Sneha, madam. Okay. I think I should remove her and I will present myself. That is better.
I will present it.
Connectivity.
Sir,
Okay, madam, you have it? Okay,
Yes, sir.
okay, okay. This is for Naveen Shankar, sir. Naveen, thanks a lot. Thank you very much. Hello, Naveen is there? Oh, now Naveen is not there, I suppose. She knows that Naveen has left. Okay,
Yeah,
yeah, I think he logged out. So, okay, yeah, but he was, whatever the coordination between you and him is really excellent. Because you are at other place, he's at other place, you are telling him and he's clicking properly. So thank you very much. Feedback is very good, excellent, and I'm happy. The way we planned this analog session went very nicely. Thank you very much, sir, and looking forward for our mixed signal design sessions as well. We have a mixed signal design sessions no, in the month of December. So
Sure.
at December starting, we are looking forward for that also, sir.
Sure, sir. Sure, sir. Thank you.
Okay.
Thank you.
Okay, thanks. Thank you, sir. Thank you very much. Thanks a lot.
Yeah. So on behalf of Entuple, thank you very much for giving us an opportunity. So thank you everyone, especially for Sardar Vallabhbhai Patel, Dr. Technology. Thanks, sir.
Okay, sir. Okay. Thank you, sir. Thanks a lot.
Yeah. Thanks.
Okay. Bye.
Thank you very much. Thanks for the patience. Thank you.
Okay. So, other participants, I understand that we are delayed today. Then a small case study has been planned for you. So I request you to come back after, let us say, 20 minutes. We will have a discussion on that. After 20 minutes, okay? So now you can take a break for 20 minutes.